So, if you've watched the first several of these videos already, just back to back to back, you might pause and take yourself a break. Normally when I teach this course in the summer, we meet for roughly 3 hours, 2 days a week, because it's a 3-hour class in an 8-week format, so it moves fast. So I guess what I'm saying is keep in mind how long you've been sitting here. Your attention span, even as hard as you try, is probably going to give out, and get up, use the restroom. What I'm saying is this is normally where I would give my students a break. If you've been watching these videos straight so far, this is normally where I would give my students a break and say, okay, go use the restroom, get you something to drink, come back, so that way you're not just completely exhausted when we get to the end of Lecture 2. Basically, we would be starting Lecture 2 at this point. So, pause the video, go take yourself a break, come back. Okay, let's continue. So, let's see. We should be able to just about get done with Chapter 1. By the way, you've got homework already assigned for Chapter 1. That's due Thursday this week, so get that in. There's a late policy. I try to be pretty forgiving, but we also have to keep moving, and it's just going to pile up on you if you don't get it done. So, what do we got here? Temperature. Again, 3 properties we can feasibly measure: volume, temperature, and pressure. We've talked about volume. Let's talk about temperature. What does it mean to be hot or cold? You probably already got an answer to that as you've been staring at that question for a while. What does it mean? I'm going to drop my pen. Sorry about the crash there. What does it mean to be hot or cold? Well, it's more of a feeling, really. Right? If I say that I'm hot, if I go outside right now, it's in the mid-90s or so, low 80s, mid-90s. I'm sorry, high 80s, mid-90s or so. I'm probably going to be warm, especially if I get out in the sun. I'm going to feel warm. What does that mean? That means your body is, the sensors in your body are telling you, the nerves are telling your brain, you're taking on heat. There's heat coming into the body, right? And what does that mean in terms of temperature? Well, what we can use temperature for is to basically measure the direction we would expect heat to flow. Now, how do we measure that? Well, we measure it using other properties. We measure it in an old school thermometer. We would measure the volume of a liquid within a vacuum, and as that liquid takes on heat, it wants to expand into the vacant portion of the vacuum, and as it expands, we can predict the rate at which it expands. Okay? There are the little ray guns, the little infrared sensors that you can basically point. It shoots a laser, and then it also is measuring the activity of a surface, and that it can equate that back to a temperature value. You've got thermocouples that's measuring basically a voltage difference between 2 pieces of metal as one metal expands into the other. So, unless you really understand how temperature is being measured, you don't really care. It's giving you a number. What does that number mean? Well, that number is telling you the direction that heat would flow relative to something else, relative to your body temperature or your skin temperature. It tells you the direction whether you're going to take on heat or you need to put more clothes on because you're going to lose heat. Okay, so it's a way of measuring the direction that we would predict heat will flow. We know from experience if I put hot food in a room that's cooler, or if I put it in a refrigerator, that food is going to cool down. It's going to lose heat to the lower temperature bodies. If I put a cold, a piece of ice, something cold, and I put it in a room, as long as that room's not a freezer, that ice is going to melt because it's going to absorb heat because the ice is at a lower temperature than the room. Okay. The system, if I put a system in surroundings that are at a different temperature, the system and the surroundings will attempt to reach equilibrium. Equilibrium, one of those terms I said we're probably not going to have time to talk about. Make sure you look at it on your own time. So the idea there is, so I forgot I've got this graphic here. So let's say I've got 2 different chunks of metal, and if I put some kind of insulation around them, so anytime you see this gray shading around something, that's insulation. We've tried to remove the ability of the system to share heat with its surroundings. So if I insulate a hot chunk of iron and a cold chunk of copper, and I just leave them together and insulate them from their surroundings, then they're just going to exchange heat with each other, and the iron is at the higher temperature. So it's going to dump heat into the copper until they reach an equilibrium, which we say that's the same temperature. And so the same temperature, that means there's no net heat flow between the two bodies. Okay. Now we've already mentioned the first two laws of thermodynamics. This is the zero law. I think I've said there are 4 laws of thermodynamics. This is what we call the zero law. Why is it zero? I don't know. I guess we came up with it after the fact, and we went back and said, well, this comes before the first law. Who knows? I haven't studied the history on this, but it's just a statement. It's not an equation that we're going to do anything major with. It's just the statement that stands on its own. We can't prove this using the first or second law or any other laws of physics, so we just have to, it has to stand as its own law, as its own theory, so to speak. If two bodies are in thermal equilibrium with a third body, then they are in equilibrium with each other. Again, if there's no source on a direct quote, that's a direct quote from your text, Changel and Bowles, 9th edition Thermodynamics. So if two bodies are in thermal equilibrium with a third body, that means they have to be in equilibrium with each other. So what that means is if I've got 2 pins here, because I always have a bunch of pins, I always seem to run out. So I've got 2 pins here, and they're both in equilibrium with the air surrounding them, their surroundings. That means they are also in equilibrium with each other. And again, there's no real way to prove that mathematically with anything other than the zero law itself. Now we talk about how do we measure this property of temperature. Well, we've got multiple scales that we can use. There is, if you've grown up outside the United States, you probably think in a Celsius scale. So in Celsius scale, water freezes at 0 C and boils at 100 C. If you've grown up here in the States, you probably think in Fahrenheit. I think in Fahrenheit. I have to convert to Celsius myself. In Fahrenheit, water freezes at 32 degrees Fahrenheit and boils at 212. Now keep in mind, this is at 1 atmosphere of pressure. We're going to talk about pressure next. That's the third property we're going to talk about. But let's finish talking about temperature. So how do we measure temperature? Well, Fahrenheit, Celsius, or Kelvin and Rankine. Right? So Kelvin is what we call an absolute scale. You should have seen that in the chemistry class. It does not have negative values. It's what we call an absolute scale or a thermodynamic scale. 0 Kelvin is what we call absolute zero. That is the lowest possible temperature, the point where all molecular motion stops. This is going to be important when we talk about the third law of thermodynamics later in the semester. Rankine is another absolute scale. Rankine has no negative values. 0 Rankine is 0 Kelvin, is absolute zero. Now, so it's always okay to use Kelvin and Rankine in this course. It's not always okay to use Celsius or Fahrenheit. Now, there's a very common situation where we can use Celsius and Fahrenheit. When in doubt, feel free to convert to Kelvin or Rankine. How do we get there? Well, Rankine is 460 degrees below Fahrenheit. The same way Kelvin is 273 degrees below Celsius. Okay? And maybe I said that wrong, but that's okay. Right? And to go between the two, I'm assuming you've done this conversion before, that's 9/5. So 9/5 of the Celsius temperature plus 32 gets you to the Fahrenheit temperature, and you can do some algebra to go back the other way. Because the y-intercept, so to speak, the 0 point is the same for Kelvin and Rankine, it's only the 9/5 or 1.8 is all you have to do to get between those two scales. So it's pretty easy to go between those two, although I can't think of very many situations where you would. A change in Fahrenheit is the same as a change in Rankine, right? So if I've got, let's say I've got, let's do ink here. Actually, let's just put, we'll do this on paper. So change in Fahrenheit, so temperature change, delta T. If I've got 10 degrees Fahrenheit, and let's say this is T2 minus T1. So I've got 10 degrees Fahrenheit minus 0 degrees Fahrenheit. So let's say I'm going from 0 Fahrenheit up to 10 Fahrenheit. Well, this is, if I convert those to Rankine, I add 460. So this is 470 Rankines minus 460 Rankines. In both cases, right, it's 10 degrees Fahrenheit or 10 Rankins. So a change in temperature is the same. This is when it's okay to use Fahrenheit, is if I'm dealing with a change in temperature, I can use Fahrenheit values because I would get the same if I converted to Rankine. Okay? Same thing with Kelvin. You probably saw this in the chemistry class. If I'm dealing with a change in temperature, I wouldn't have to convert to Kelvin. I could just take the difference in the Celsius temperatures, and it would give me the same difference I would see in Kelvin. Same thing with Rankine and Fahrenheit. Add 460 to the Fahrenheit to get to Rankine. Do that to both. It just subtracts out. Change in Fahrenheit is a change in Rankine, and a change in Celsius is a change in Kelvin. Okay? All right. What else here? No ink on that one. And that brings us to pressure. Where am I at in time? Okay. Well, we can get started. There's no sense in stopping there. So if we talk about pressure here, right? So we talk about pressure. Pressure is measured as force per unit area. It is the result of, if I've got some kind of fluid, let's say I've got water here, okay? And if you put an object, let's say we put a person, and I'm not going to draw a person, but let's say we put some kind of object submerged in this water, okay? That pressure is going to exert a normal force in all directions. So there's no direction to it, it's just perpendicular to whatever surface it comes in contact with, right? So if I take the area of this surface and if I take the total force that the liquid, or in this case the water, is applying to a diver, let's say you go dive down in a pool or a lake, you're going to feel a force applied to your skin. And if you divide that force per area, divide the area that fluid's coming in contact with, that is the pressure that's resulting on your body at that point. Okay? And as you go further down, we know that increases. Now, if we look at units there, right? So if we look at the units associated with pressure, 1 Pascal is 1 Newton per meter squared. Now, one thing you'll want to start getting comfortable with is being able to break units down into their base units. So we know a Newton is a unit of force. Yes, Izzy, we're recording. Thank you. Sorry, my cat does that sometimes. Again, the Newton is the unit of force. Force is mass times acceleration. So 1 Newton is a kilogram meter per second squared. That's a Newton per meter squared. No, I can't hold you right now. You're fine. This will be throughout the semester. Sorry. So, if I do some algebra here, this becomes 1 kilogram per meter second squared. And that's 1 Pascal. So notice, again, I don't expect you to have this memorized. There's no reason to memorize this. All you have to memorize is that, well, pressure is force per area, so that's newtons per meter squared. Right? It's easier to think about pressure as force per area than it is a Pascal as a Newton per meter squared. And it's easier to think about, well, a Newton is force, so therefore it's mass times acceleration. That's probably easier to remember than a Newton is a kilogram meter per second squared. I find it easier to remember. However works for you. Just be able to break a Newton down into a kilogram meter per second squared, and then we do some algebra and get it down to, I don't have to memorize this, as long as I understand this is force per area, and force is mass times acceleration. That's what works for me. Anyway, you need to be comfortable doing that. All right, that's my timer. We'll start another video, and we'll go to the next units. All right, so you're going to hear pop.